Greetings, everybody. We are still skimming the book Problem Solving in Data Structures and Algorithms using C++. We reached chapter 21. It's about the complexity theory and NP completeness. The complexity theory and NP completeness. Introduction. Computational complexity is the measurement of how much resources are required to solve some problem. How much resources do we need to solve this problem? What are the resources? There are two types of resources. Time and space. Time is how many steps it takes to solve a problem, assuming the step is a fixed, like it's a CPU cycle or something like that. It's fixed. So how many steps means this number of steps is an indication of how long. All right, so it's the time, how long, and how much memory it takes to solve a problem, and the storage. So the time and the space. The time required to accomplish something, the space needed to accomplish something. In real life, if I want to build a table from wood, how long it will take me to do that, and the space, like how much space do I need. Of course, in both cases we are assuming the same abilities, the same skill set, right? The same hardware. Decision problem. Much of complexity theory deals with decision problems. A decision problem always has a yes or no answer. So the decision in the flowchart is that trapezoid that has the yes and no output. Many problems can be converted to decision problem, which have answered as yes or no. For example, searching. So we will take 4 examples, I guess. The first one is searching. The problem of searching element has a decision problem if we ask to find it, to find if a particular number is there in the list. Yes, we found it. No, we didn't find it, right? Sorting. Sorting of a list to find if the list is sorted, you can make a decision problem. Is that list is sorted in increasing order or not? So if it's in increasing order, yes, otherwise no, right? So we convert a problem into yes and no style. Graph coloring algorithms. This is also can be converted to a decision problem. Can we do the graph coloring by using X number of colors? Yes or no, right? Hamiltonian cycle. Is there is a path from all nodes. Each node is visited exactly once and come back to the starting node without breaking. Yes or no? Do we have a Hamiltonian cycle? Yes or no? Right? Complexity classes. So we have several classes depending on the complexity. And if I'm not mistaken, there are 4 classes: the P, NP, hard P, and we'll see the rest. Problems are divided into many classes such that how difficult to solve them, or how difficult to find if the given solution is correct or not. To confirm the correctness of the solution, or to decide is it difficult or not. So the first one, class P problems. Class P. The class P consists of a set of problems that can be solved in a polynomial time. Polynomial time. So if it can be solved in a polynomial time, then this is called class P problems. The complexity of a P problem is a function of n to the power of k, where n is the input size and k is some constants that can't depend on n. Class P definition: the class P contains all decision problems for which there exists a Turing machine algorithm that leads to yes and no answer in a definite number of steps by a polynomial function. For example, given a sequence a1, a2, a3 until an, find if a number x is in the array. We search the number x in the array in a linear time polynomial time. So polynomial time means linear time. This is the very first type of problem, is the class P, polynomial. That's a linear time, all right? Another example, given a sequence from A1 to AN, if we are asked to sort the sequence, we can sort and array in a polynomial time using bubble sort. This is also linear time, polynomial, all right? So the logarithm, if it's a function of the logarithm of n, it's also polynomial. So if it's a linear, it's a polynomial. If it's logarithm of n, it's polynomial. Any algorithm which has complexity less than some n to the power of k is also polynomial. So anything less than n to the power of k is a polynomial. So if it's a linear, it's a polynomial. It's a logarithmic, it's a polynomial, or anything less than that is a polynomial. Some problem of class P. By the way, if we select the brute force, it will be square and square. But we selected bubble sort, not brute force sort. So it became polynomial, right? Some problems of P class is the shortest path, the minimum spanning tree, the maximum problem, the maximum flow graph problem, the convex hull problem. So all these are P class, polynomial, less than, right? Less than n to the power of k. Now we'll move to the next class. We are done with the class P. Now we have class NP. Set of problems which there is a polynomial time checking algorithm. Set of problems for which there is a polynomial time checking algorithm. So they have a polynomial time checking algorithm for which there is a polynomial time checking algorithm. The checking algorithm takes polynomial time. Given a solution, if we can check in a polynomial time, if that solution is correct or not, then the problem is NP problem. Now, if we can check in a polynomial time, it's NP. Class NP definition. The class NP contains all decision problems for which, given solution, there exists polynomial time proof or certificate that can verify if the solution is the right Yes or no answer. All right. So if we look, the polynomial time is subgroup of the NP. So the NP is more general. The P class problems is subgroup of that, right? There is no guarantee that you'll be able to solve the problem in a polynomial time, but if a problem is an NP, then you can verify an answer in a polynomial time. Not solving it, but verifying it. The verification, if you can do it in a polynomial time, then it's an NP class problem. All right, let's move. NP does not mean non-polynomial. Does not mean none. Actually, it is non-deterministic polynomial type of a problem. They are the kind of problems. They are the kind of problems which can be solved in a polynomial time by a non-deterministic Turing machine. At each point of all possibilities are executed in parallel. If there are n possible choices, then all n cases will be executed in parallel. We don't have non-deterministic computers. Don't confuse with the parallel computing because the number of CPU is limited in parallel computing. It may be 16 core or 32-bit core, but it can be n core. So don't confuse it with a parallel computing. Don't confuse it with a parallel computing. We are not talking about the parallel processing, right? We're talking about the classes of problems. In short, NP problems are those problems for which, if a solution is given, we can verify that solution in a polynomial time. This is the complete definition for NP problems. Let's read it one more time. In short, NP problems are those problems for which, if a solution is given, we can verify that solution in polynomial time. We can verify that solution if it's correct or not in polynomial time. All right, we are done with that part. Let's see about the Boolean satisfiability problem. A Boolean formula is satisfied if there exists some assignment of the value zeros and ones to its variables that causes it to evaluate to 1. All right, Boolean expression. There are in total n different Boolean variables from a1 to an. There are an m number of brackets. Each bracket has k variables. There is an variable, so the number of solutions will be 2 to the power of n. And to verify if the solution really evaluate the equation to 1, will take n to the power 2 to the power n times km steps. Given solution of this problem, you can find the formula satisfied or not in km steps. Polynomial can be verified in polynomial time. Hamiltonian cycle. Hamiltonian cycle is the path from all the nodes of a graph. Each node is visited exactly once and come back to the starting point without breaking. Like you start, visit every single point and come back to exactly to the same spot without revisiting, without crossing what you passed on, right? F is an NP problem If you have a solution to it, then you just need to see if all nodes are there in the path, and you come back to where you started and you are done. The checking is done in a linear time and you are done. The checking, not the solution. You have the solution of the Hamiltonian cycle, but you would like to check, verify. Determining whether a directed graph has a Hamiltonian cycle does not have a polynomial time algorithm. The solution takes factorial n. However, if someone have given you a sequence of vertices, determining whether or not that sequence forms a Hamiltonian cycle can be done in a polynomial time or linear time. Hamiltonian cycles are in NP. But verifying only can be done in a polynomial time, right? A click problem in a graph given is there is a click of size k or more. A click is a subset of nodes which are fully connected to each other, fully connected. This problem is an NP problem. Given a set of nodes, you can very easily find out whether it's a click or not, right? Confirming it, verifying it, can be done this way. Click of size 4. A, B, D, E. So we are taking examples of NP problems. The next one will be the prime number. Let's go back for a second. Let's go back for really quick here. So after we started with the NP, class NP, and we described how it's related to the P, class P, and how it's more generic, and it's about verifying, not solving, in polynomial. We took the Boolean satisfiability problem and the Hamiltonian cycle problem. All these are NP class. And then we took the click problem. It's also NP class. And next we'll talk about the prime number problem, which is also an NP class, right? Finding prime number is NP. Given a solution, it's easy to find if it's a prime or not in a polynomial time. If you have the solution, it's easy to verify, to confirm it in a polynomial time. So it's an NP, right? Non-deterministic P. Finding prime numbers is important as cryptography heavily uses prime numbers. Why do we need to find prime numbers? Because cryptography heavily uses prime numbers because we need it in the cryptography, like encryption, right? Cryptography. So this function is prime, true, false. So it uses the ternary operator here. This is C++ ternary operator, right? The question mark and the colon. And here is a for loop, and it confirms if the modulo equals to 0, then the answer is true, and return the answer. Like no remainder, no division remainder, right? Check-in will happen till the square root of the number. So the time complexity will be a function of square root of n. Hence, prime number finding is an NP problem. We can verify the solution in polynomial time. Can verify. So this is NP class problem. A graph theory have wonderful set of problems. Graph theory have wonderful set of problems. Shortest path algorithms. Longest path is NP-complete. Eulerian towers is a polynomial time problem. Hamiltonian tours is an NP-complete. So we are done with the P class and with the NP class. Now we are coming to the third one, which is called Co-NP. Co-NP class, right? This is the third class. Set of problems for which there is a polynomial time checking algorithm. Set of problems for which there is a polynomial time checking algorithm. Given a solution, if we can check in polynomial time if the solution is incorrect, the problem is co-NP. It's very close to the NP. It's not verifying. It's checking. Class NP. Class co-NP definition. The class co-NP contains all decision problems such that there exists a polynomial time proof that can verify if the problem does not have the right yes or no answer. So we have the P class in the middle, we have the NP, and the P is a subgroup of the NP, and we have the co-NP, and the P also is a subgroup of the co-NP, and they have this shared area in the middle, but they do not match. The NP verify, the co-NP checks, right? Class co-NP definition. The class co-NP contains all decision problems such that there exists a polynomial time proof that can verify if the problem does not have the right yes and no answer. Does not have the right. All right. Class P is a subset of class NP, as shown from the figure from previous title or header. We talk about the NP, now we are talking about the co-NP. Now, going back to the NP, right? We see that the class P is a subset of the class NP. All problems which are P are also NP. Problem set P is a subset of problem set NP. Searching, if we have some number sequence from A1 to AN, we already know that searching number X inside this array is of type P. If it's given that the number X is inside the sequence, then we can verify by looking into each and every entry again and find if the answer is correct in the polynomial time. That's the NP, right? So this shows how the searching is both P and NP. Solving it and verifying it, right? And we have the second example, sorting. Sorting, another example of sorting a number sequence. If it's given that the array from B1 to until B3 until Pn is sorted, then we can loop through this given array and find if the list is really sorted in a polynomial time. Is really sorted, and it will take a polynomial time, which is in both cases linear time, and this is the searching is both P, class P, and class NP, right? So now we covered three classes, the P, the NP, the co-NP. The fourth class is the NP hard. A problem is NP-hard if all problems in NP can be reduced to it in polynomial time. Can be reduced to it in polynomial time. Can be reduced to it in polynomial time. A problem is NP-hard if all the problems in NP can be reduced to it in polynomial time. What's the class of the NP-hard? A problem is NP-hard, or its class lies in the class NP-hard if all the problems in NP class can be reduced to it, to the NP-hard, in polynomial time, as shown in this figure here. This is the NP class, and the P class is a subgroup or subset of it, and we can reduce it to NP-hard. NP-complete problems. So we are done with the P, with the NP, with the co-NP, and with the NP-hard. Now we have the NP-complete problems. What is this? What is the NP-complete problem? It's a set of problem. A set of problem is NP-complete if it is an NP problem and also an NP-hard problem. If it's an NP problem and an NP-hard problem, then it's NP-complete. NP problem, we can verify it in polynomial time. NP-hard, we can transform the NP problem to the NP-hard in polynomial time. If it's both NP and NP-hard, then it's NP-complete. It should follow both the properties. Its solution can be verified in polynomial time, can be verified, so it's NP. All the problem of the NP are reduced to NP-complete problems in polynomial time. And NP-hard, I think, can be reduced to NP-hard. Yes, NP-hard. This should be NP-hard, right? This complete should be hard. I think this is a typo. All right. You can always reduce any NP problem into NP-complete. You can reduce any NP problem to NP-complete in polynomial time. You can always, as a conclusion, you can always reduce any NP problem into NP-complete in a polynomial time, of course, because if it's at the same time NP and NP-hard, then it can be reduced to NP-complete in polynomial time. And when you get the answer to the problem, then you can verify the solution in polynomial time, because NP-hard can be verified. So we have the P class here, the NP is here, is more general, and the NP-hard on the top, that we can transfer NP to NP-hard in polynomial. If it's at the same time NP and NP-hard, then it's this region in the middle here, right? The common ground, the common region. So NP reduction, NP-complete. Any NP problem is a polynomial reduced to NP-complete problem. Any NP problem is polynomial reduced to NP-complete problem. If we can find solution to a single NP-complete in polynomial time, then we can solve all the NP problems in polynomial time. But so far, no one is able to find any solution of NP-complete problem in a polynomial time. No one. But so far, no one is able to find any solution of NP complete problem in polynomial time. And this is a challenge for the reader. If you can do this, you'll be the first one to do it. So the P doesn't equal the NP. It's a subset, but doesn't equal it, right? Reduction. It's a process. What's the reduction? It's a process, this is the definition. It's a process of transforming of one problem into another problem. Reduction is a process of transformation of one problem into another problem. The transformation time should be polynomial. If a problem A is transformed to B, problem B, and we know that solution of B is polynomial time, in polynomial time, then A can be solved in polynomial time. Reduction, right? Transformation. For example, quadratic equation solver. We have a quadratic equation solver which solves equation of the second degree, the quadratic, right? So it's A times x squared plus b times x plus c equals 0. It takes the input A, B, and C and generates output R1 and R2. Now try to solve a linear equation 2x plus 4 equals 0 using reduction. Second equation can be transformed to the first equation by adding A equals to 0. So we have 0x2 x to the power of 2 times 2x plus 4 equals 4, right? And this way we can apply the same solution. Now, atlas in the globe map, we have an atlas and we need to color map so that no two countries have the same color. In this page, we use the different patterns representing different colors. So this is the square pattern, this is the diagonal, this side, and this is like wavy, yeah, like star, whatever. Yeah, so different patterns are representing different colors. We can see the same problem of atlas coloring can be reduced to graph coloring, and if we know the solution of graph coloring, then the same solution can work for atlas coloring too. There, where each node of the graph represents one country and adjacent country relation is represented by the age between nodes, just like that. So we transform this into this. The sorting problem reduced to convex hull, the SAT reduced to 3 SAT, and in this way we did problem reduction, right? We transformed the problem to another problem. Let's take another example. That's traveling salesman problem, TSP, traveling salesman problem. The traveling salesman problem tries to find the shortest tour through a given set of n cities that visits each city exactly once. So if you do it on the paper, you don't cross the same dot again because you visited only once before returning to the city where it started. So this is called traveling salesman problem, TSP. Alternatively, finding the shortest Hamiltonian circuit in a weighted connected graph, a cycle that passes through all vertices of the cycle exactly once. So we have shortest Hamiltonian circuit is very similar to the traveling salesman. So we can transform first to the second, right? And this is called reduction. Total number of possible combinations is n-1 factorial. The cost for calculating the path is a function of n, theta of n. So the total cost for finding the shortest path as a factorial, as a function of n factorial, n factorial, right? It is an NP-hard problem. There is no efficient algorithm to find its solution, right? Even if some solution is given, it's equally hard to verify that this is a correct solution or not. But there are some approximate algorithms which can be used to find a fairly good solution. We will not always get the best solution, but we'll get fairly good solution. Our approximate algorithm is based on the minimum spanning tree problem. So we want an approximate solution in which we have to construct a tree from a graph such that every node is connected by edges of the graph and the total sum of the cost of all edges is minimum. And this is called minimum spanning tree. In the above diagram, we have a group of cities. Each city is represented by a cycle, which are located in the grid, and the distance between the cities is the same as per the actual distance. There is a path from each city to another city, which is a straight path from one to another, just like that. We have made a minimum spanning tree for the above city graph. What we want to prove is that the shortest path in TSP, traveling salesman problem, will always be greater than the length of the MST, minimum spanning tree. Since all nodes are connecting to the next node, which is the minimum distance from the group of nodes, so some node is removed and new nodes will be added to make it a path, so TSP path will always be greater than MST, just like that. Now let's take a path from starting node and traverse each node on the way given above and then come back to the starting node. The total cost of the path is 2 MST. The only difference is that we are visiting many nodes multiple times. Now let's change our traversal algorithm so that it will come TSP, traveling system, in our traversal. We did not visit an already visited node. We will skip them and will visit the next unvisited node. In this way, we'll have reached the next node by shorter path. The sum of lengths of all the edges of the polygon is always greater than a single edge. Ultimately, like this is what we've done. Ultimately, we'll get the TSP and its path length is no more than twice the optimal solution. So the proposed algorithm gives a fairly good result. So this is a fairly good result based on the minimum spanning tree, right? And this is called the TSP, traveling salesman problem. And nobody has come up with such a polynomial time algorithm to solve NP-complete problem. Many important algorithms depends on it, But at the same time, nobody has proven that no polynomial time algorithm is possible. There is millions of US dollars for anyone who can do either solve any NP-complete problem in polynomial time. The whole economy of the world will fall as most of the banks depends on the public key encryption will be easy to break if P equals to NP solution is found. That was the end node of the chapter, and we'll see you in the next video in chapter 22, which is about the interview strategy. This is a cool and interesting chapter. See you later.